As a quick preview, the primary focus of our work lies in enhancing the local features of the standard MLP. Like this picture, in contrast to other dynamic aggregation methods, our approach introduces a novel representation that guides the process of feature aggregation. Our motivation stems from the weighted summation mechanism employed in MLPs, which is commonly used in methods for weight assignment. We consider the input feature vector component as a high-dimensional vector containing only a single non-zero value. Naturally, it is reasonable to imagine that each feature component is transformed in a high-dimensional space. It can be observed that the 1D vector transformation solely involves scale transformation, whereas the 2D vector transformation introduces an additional rotation operation. First, let's introduce the preliminary contents. These observations highlight the requirements that must be met for effective point cloud feature extraction. Consequently, we adopt a similar component to PointNet, as it naturally fulfills these requirements. For the input features, it is intuitive to perceive each channel value in an n-dimensional feature vector as a coordinate value along a specific axis, akin to a basis vector pointing in the direction of that axis. By interpreting the weighted summation from the vector perspective mentioned earlier, it is reasonable to deduce that higher dimensional vector transformations can lead to more intricate and sophisticated representations. Higher dimensional vectors naturally accommodate a wider range of transformations and provide a more effective means of representing intricate neighbor relationships. The challenge of reconciling the relationships between neighboring features using scalar weights is transformed into a problem of vector summation. This approach enables the incorporation of homogeneous promotion, reverse inhibition, and vector orientation, facilitating a more expressive representation of their relationships. The vector transformation consists of a scaling transformation and a rotation transformation. One parameter can be represented the scaling factor. The transformation of 3D rotation involves rotating around a specific axis, necessitating the determination of both the rotation axis and the rotation angle. In accordance with Euler's theorem, this rotation can be decomposed into 3 successive rotations around orthogonal axes. Since we assume that the feature components lie on the coordinate axis, a rotation parameter can be omitted. Only 2 rotation angles are needed to represent this rotation. These 2 formulas define how to obtain the intermediate vector representation to implement the composite operation of scaling and rotation. Since the vector transformation alone is completely linear, we choose to add ReLU to increase the nonlinear factor when predicting the rotation angle. Our network structure is akin to PointXT and is divided into 3 scale models. We denote C as the channel of embedding MLP in the beginning, S as the numbers of the SA module, V as the numbers of the VPSA module. The utilization of vector-guided feature aggregation results in a substantial performance enhancement, accompanied by a notable reduction in both parameter count and computational requirements. However, due to optimization challenges, it exhibits a slight lag in terms of speed. Although our setup differs significantly from stratified former, we still maintain a slight advantage over it. Validation results for other benchmark datasets and ablation experiments are detailed in the paper. Conclusion. 1. We propose a new perspective on the weighted summation operation. 2. Indeed, we propose the adoption of intermediate vectors to represent the aggregation of neighboring features, guided by the direction indicated by the vector. 3. For the vector transformation operation, we propose a construction method for the rotation matrix utilizing independent rotation angles, in accordance with Euler's theorem. Limitation. The speed of our approach is constrained by the grouped convolution implementation. We have not delved into deconstructing the representation of rotation in four-dimensional space, which becomes more intricate, particularly within the plane. Additionally, summing after component alignment aligns with our assumptions better than scalar projection. As shown below, each channel should be aligned and then summed directly.